Chapter 15, Regression. Section 15.1, Introduction to Regression. Regression is one of the most important techniques in the statistician's toolbox, along with the t-test, correlation, and ANOVA. Regression is an umbrella term. There are many variants of regression that have somewhat different models, assumptions, and estimation procedures. The main focus of this chapter is linear regression, and I will introduce some regression variants towards the end of this chapter. A linear regression is a solution to a model of the data that predicts the observed data, often indicated by y, based on a linear combination of IVs, often indicated by x sub k for the kth independent variable, plus a residual term often indicated by the Greek letter epsilon. Linear regression models have the following general form. Here we have equation 15.1, which reads y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus ... beta k xk plus epsilon. Those beta terms are called coefficients or beta values, and are scalars that encode the contribution of each IV to explaining the dV. The rest of this chapter is basically just a detailed explanation of equation 15.1, but for now, suffice it to say that a regression involves predicting a dV, that's variable y, using a linear weighted combination of the IVs, where beta are the weights and x are the IVs, and that the goal of a regression analysis is to find the betas that minimize the unexplained variability, that is the Greek character epsilon. The epsilon term is often omitted when showing the equations because it's understood that the models never capture all of the variability in the dV. What is linear? What makes a linear regression linear? A linear regression is based on linear operations, in particular element-wise multiplication and summation. Linearity allows for an elegant, fast, and deterministic solution that we can prove is optimal. Linear regression is a workhorse of data analysis, and linear should not be confused with limited. Now, to be sure, there are some limitations of linear regression which can be addressed using nonlinear models that I will discuss toward the end of this chapter. The linearity constraint is limited to the beta terms. The IVs can have nonlinearities. For example, consider the following two models. Here we have two equations. Equation 15.2 reads y equals beta 0 plus beta 1 x1 plus beta 2 times the quantity x2 times x1 plus beta 3 times the natural log of x1 times the square root of the quantity 3 plus x2 plus epsilon. Then we have equation 15.3, which reads y equals beta 0 plus 1 over e to the minus beta 1 x1 plus beta 2 cubed times x2 plus the natural logarithm of the fraction beta 3 times x1 divided by x2 plus epsilon. Equation 15.2 is a linear regression model. There are nonlinear transforms on the IVs, but the only operations acting on the beta values are multiplication and sum. In contrast, equation 15.3 is not a linear regression model because nonlinear operations are applied to the beta coefficients. To be clear, nonlinearities in the coefficients can be interesting and are used in many applications, but nonlinear models require nonlinear methods for fitting, and those are beyond the scope of this chapter, except for some brief discussions towards the end. Regression versus GLM. GLM stands for General Linear Model. Footnote. Confusingly, GLM also stands for Generalized Linear Model, which is a different statistical modeling approach that incorporates nonlinear functions and estimation algorithms. End footnote. GLM is an umbrella term that incorporates many analyses discussed in this book, including t-tests, ANOVAs, and regression. Broadly speaking, the goal of a GLM is to model observed data using a linear combination of IVs plus a residual term. Therefore, a regression analysis is one type of GLM. Regression versus ANOVA. Regression and ANOVA are similar in that they are linear models that aim to explain a DV based on combinations of IVs. Indeed, they are both specific cases of GLM. The key difference is that ANOVAs are designed to explain means across categories, whereas regressions are designed to explain variability within a sample. This is analogous to the difference between a t-test and a correlation. How do you know whether to use an ANOVA versus a regression? If you have multiple IVs and at least one is continuous, then use a regression. If all IVs are categorical, then use an ANOVA. Regression versus correlation. Regression and correlation are similar in that they quantify the linear relationship between continuous variables. There are two key differences between regression and correlation. First, regression is extendable to predicting the DV based on multiple IVs, whereas correlation is defined only for two variables. Second, regression can quantify the relationship between two variables in the scale of the data, whereas the correlation coefficient is normalized. In Chapter 12, I showed an example of the distinction between correlation and regression slope. That was figure 12.3 on page 392. Regression and causality. A regression analysis does not provide evidence for a causal relationship for the same reason that a correlation does not provide evidence for causality. However, regression does provide more opportunities for testing causal relationships, such as using data from the past to predict data from the present. This would be called an autoregressive model. Nonetheless, the best way to establish causality is with proper experiment design supplemented with appropriate statistical analysis. Assumptions of regression. Yes, of course, there are assumptions of a regression analysis. Most of the assumptions are the same as those for other parametric statistics. A detailed section on assumptions, along with possible mediating strategies to deal with violations of assumptions, comes towards the end of this chapter. Section 15.2, Regression Terminology and Notation. Regression has its own set of terms and notations. Some of these terms are identical or similar to terms you are already familiar with, while others may be new to you. Each of the terms below will be discussed heavily and repeatedly throughout this chapter, so familiarize yourself with the concepts below, but don't stress about memorizing or fully understanding them now. Regressors. Regressors are the IVs in a regression model. They are sometimes called predictors or explanatory variables. Intercept, also called the constant term. This is a regressor of all ones. That is, the value of one is predicted for each data observation. The term itself is left implicit in regression models and is associated with the beta 0 term. The interpretation of the intercept is the value of the DV when all IVs are set to 0. Consider what happens when all the x terms are 0 in equation 15.1. In many applications, the intercept term is not interpreted, but it must be included in the model for reasons I will explain later in this chapter. Beta terms. These are the unknown parameters that we seek to estimate. In different contexts, they are called coefficients, weights, scalars, unknowns, beta values, fitted parameters, or some combination of those words. I will have more to say about interpreting those beta values throughout this chapter, but briefly, the interpretation of beta 1 is the amount of change in y per unit change in x1 while holding all other variables constant. You'll often see subscripts on the regressors to facilitate interpretation, like beta sub height or beta sub income. Technically speaking, the beta coefficients are scalars and do not have units on their own. But because each beta is attached to one variable, beta 1 and beta 1 x1 have the same units. Therefore, we can colloquially speak of the beta coefficients as having the units of their associated variables. I will return to this discussion in the section on computing and interpreting standardized beta coefficients. Interaction. A regression model may contain interaction terms which are indicated as a multiplication between the two variables with one unique coefficient. For example, y equals beta 1 x1 plus beta 2 x2 plus beta 3 times the quantity x1 times x2. This is not mere notation, however. An interaction term is literally defined as the product of two terms. Beta 3 has the same interpretation as the interaction term in an ANOVA. The effect of x1 on y depends on the values of x2. Also, as with ANOVA interactions, main effects can be difficult or impossible to interpret in the presence of a significant interaction, and visual inspection is required. Design matrix. The design matrix is an n by k matrix in which each column corresponds to a regressor and each row corresponds to an observation. There's no necessary ordering or sorting to the columns. They can be arranged randomly or according to some characteristic of the experiment design. The design matrix is indicated using capital boldface X, and thus the matrix regression equation is boldface Y equals boldface capital X boldface beta plus boldface epsilon. Boldface beta is a vector of regression coefficients. Non-boldface beta is an individual coefficient, so one element of the vector boldface beta. Simple versus multiple regression. This distinction corresponds to the number of regressors. A simple regression has two regressors, the intercept and one IV, whereas a multiple regression has more than two regressors. Footnote: I cannot justify the existence of these terms. Simple versus multiple regressions have no meaningful mathematical, statistical, or interpretational distinctions. But these terms are ubiquitous in the regression world, and I have no choice but to conform. End footnote. Dummy coding. I know you're expecting me to make a joke about programmers of low intelligence. In fact, dummy coding is a method used to transform categorical variables into a series of binary, so 0 and 1, variables. For instance, the factor education could be dummy coded into two variables, high school 0 and university 1. Dummy coding is necessary because the regressors must be numeric. The mapping of category to number has implications for interpreting the results. For example, in a regression model predicting adult human height, coding sex as male equals 0, female equals 1 would produce a negative beta value indicating that the change from 0 to 1 is associated with reduced height. Whereas coding sex as male equals 1, female equals 0 would produce a positive beta value indicating that the change from 0 to 1 is associated with increased height. As with the numerator of the t-value, the sign can be chosen to facilitate interpretation, but does not affect the statistics of a two-tailed test. Predicted data. As with ANOVAs, The regression model generates a prediction of the value at each data point. The prediction is the sum of all the IVs weighted by their corresponding beta terms. The predicted values are often indicated as y with a caret symbol on top of the y. So it's like a y with a little roof over it. This is pronounced y hat. Mathematically, the predicted data are defined as y hat equals the sum of all the betas times their corresponding x's. Needless to say, if the regression model is a good fit to the data, then y hat is approximately equal to y. You will learn later in this chapter that regression models are evaluated based on qualitative and quantitative assessments of y hat and the residuals. Residuals, epsilon. The residuals in a regression are mathematically and conceptually the same as the residuals in an ANOVA. They are what remains in the DV after the best prediction from the linear combination of the IVs. In other words, epsilon equals y minus y hat. Residuals are important in regression analysis because the beta values are selected in a way to minimize epsilon. Residuals are also key indicators of poor model fit. A well-fitting model has residuals that are normally distributed, homoscedastic, and uncorrelated with the DV. As I wrote in the previous chapter, residuals are also called errors, although I dislike this term because unexplained variability is not necessarily erroneous. Footnote: I have very occasionally heard residuals referred to as residues by non-English speakers. I do like how that sounds, but it's not the correct term. Section 15.3, the picture of regression. Imagine we have one DV and one IV. We can make a scatter plot of the data that shows the key picture of regression. This paragraph refers to figure 15.1, which illustrates that regression involves fitting a line that minimizes the squared distances from each observation to the predicted value which is on that line. So we see a scatter plot where x-axis is labeled x, the regressor, and the y-axis is labeled y, or the DV. There are 9 observations depicted in this graph, indicated as a light gray circle. And then there is a regression line, that's a black line, that cuts through the data point. So this is the best fit line, and there's a positive relationship. However, the observations, the light gray dots, are not exactly on the line. And so therefore, we see some vertical dashed lines that go from each data point to the location on the line, which that indicates the predicted values, and those are indicated with gray squares, dark gray squares. And then we see one value called the intercept, labeled the intercept. It is a white triangle, and it is positioned at the x-axis at location x equals 0. This point, this intercept, does not actually correspond to any actual observation. It is just a point on the best fit line corresponding to x equals 0. Back to the text. The goal of regression is to find the line that minimizes the sum of squared distances from the data observations to that line. The squares depict the model predictions at each measured point, and the lengths of the dashed lines are the epsilons, the residuals, for each data point. Regression can also be used to make predictions about the value of the DV for data points that were not measured. This is called predictive modeling, and you'll see how easy it is in exercise 9. Indeed, one of these interpolated points is the predicted value of the DV when the IV equals 0, which is the intercept of the model. That was the white triangle at x equals 0 that I described. Regression versus PCA. Principal components analysis is a statistical technique that aims to find an axis that explains maximal variance in a multivariate dataset. It is not the same thing as regression. The reason I bring it up here is that many students wonder why regression involves projecting the data vertically onto the best fit line. Indeed, if the goal is to minimize the errors, then wouldn't the errors be even smaller if the data were projected orthogonally instead of vertically? Consider figure 15.2, which shows a regression and PCA on the same data. This paragraph references figure 15.2, which shows the same data used in a regression, that's in panel A on the left, and principal components analysis in panel B on the right. Now, both of these plots have the same data values, but the best fit line looks different between the two panels. The panel on the left is titled Errors to Minimize in Regression. And here we see that the residuals are all perfectly vertical. So the dashed lines going from the observations to the best fit regression line all go exactly up or down. They are stationary on the x-axis. They only vary along the y-axis. In contrast, in panel B on the right, we have the picture of principal components analysis. And here we see that the slope of the line is different. It's a little bit higher. And the residuals that go from the data points to the line are not vertical. They are actually a little bit diagonal. Back to the text. Here is the key difference. In PCA, there is no distinction between the independent and the dependent variable. There are simply variables. In contrast, in regression, we don't want to vary the IV, the data on the x-axis. We assume that our predictor variables are perfect and the errors are in the observations. A more mathematical way to explain this is that PCA derives a new basis vector, whereas regression retains the basis created by the columns of the design matrix, so the IVs. Section 15.4, a simple example. Imagine you saw a video on whatever social media platform is trendy when you're reading this about how eating ice cream makes you a happier person. You're unsure whether that's a real effect, and so you decide to collect some data. You randomly sample 5 people and have them report the number of ice cream cones they've eaten in the past month and to rate their subjective life happiness in the past month. Data are shown in figure 15.3. Clearly, there is a positive relationship between these two variables. You then give me the data so I can perform a regression analysis. Don't worry, by the end of this chapter, you'll be able to do the analysis yourself. This paragraph references figure 15.3, which shows imaginary data from the imaginary ice cream happiness study. Each dot corresponds to an observation, and we see a very tight relationship between the number of ice cream cones eaten on the x-axis and overall life happiness on the y-axis. That said, there are only 5 data points in this data set. Back to the text. The model I tested follows this equation. Equation 15.4 reads H equals beta 0 plus beta 1 C, where H is the level of happiness and C is the number of ice cream cones eaten. The units of beta 1 are happiness units per ice cream cone, and the interpretation of beta 0 is the baseline level of happiness for people who eat 0 ice cream cones. That is, H equals beta 0 when C equals 0. To organize the data for a regression, we start by treating equation 15.4 as a quote-unquote template model that we replace with each observation. There are 5 observations and each gets its own equation. Refer back to figure 15.3 to see how each equation maps onto each data point. So here we have 5 equations. First is 5 equals beta 0 plus beta 1 times 1. The second equation is 6.5 equals beta 0 plus beta 1 times 2. And then we have 6 equals beta 0 plus beta 1 times 4. 8 equals beta 0 plus beta 1 times 5. and 9 equals beta 0 plus beta 1 times 7. Notice that the values of the IV and DV are different for each person, but the parameters, beta 0 and beta 1, are the same. This means that each person is unique, but the relationship between ice cream and happiness is the same for everyone. The next step is to convert this series of equations into one matrix equation. Ice cream cones eaten and the intercept are the two IVs, so we put those into a design matrix. The betas and the DV go into vectors, and we form a matrix equation. Here we have equation 15.5, which shows a matrix equation of all the individual equations that I just read out. So there are three terms in this equation. The first term is the design matrix. That's a 2 by 5 matrix with ones on the first column and the number of ice cream cones in the second column. So all ones on the left, and the right column is 1, 2, 4, 5, 7. The second element in this equation is a 2-element column vector with beta 0 and beta 1. And then we have an equal sign, and then on the right is a 5-element column vector with the DV, so that is 5, 6.5, 6, 8, and 9. I then ran a regression using math and methods that you will soon learn about. The model was a good fit to the data, so we have F with 3 and 1 degrees of freedom equals 14.7, P equals 0.031. So it is possible to interpret the individual regressors, both of which were statistically significant with p-values less than 0.03. Beta 0 equals 4.6, meaning that the expected life happiness for someone who does not eat ice cream is 4.6 out of 10. The slope coefficient was 0.6, that's beta 1, indicating that for each additional ice cream cone eaten, you can expect a 0.6 increase in life happiness. We can use the beta values to predict life happiness based on ice cream consumption. The model predictions are a linear weighted sum of the predictor variables, and the betas are the weights. In other words, the predicted level of happiness is, here we have equation 15.6, y hat equals 4.6 plus 0.6c. The model results allow us to make statistical predictions for someone's life happiness based on the number of ice cream cones they've eaten, even people who have not provided any data, assuming that the sample was random and representative of the population. For example, if you eat C equals 100 ice cream cones in a month, that's about 3 each day, you can expect to have a life happiness score of 64.6 out of 10. Okay, and I admit this example is getting a bit silly. There might be a real-world relationship between life happiness and ice cream consumption, although I doubt that that relationship is causal in the way I suggested above. In fact, I can imagine that people are happier in the summer and when on vacation, which is also when they are more likely to eat ice cream. Section 15.5, Least Squares Solution to the GLM. Note: this section includes concepts and operations in linear algebra and calculus that I have not introduced earlier in the book. If you have taken courses in linear algebra and calculus, you should be able to follow along. If you do not have this background, then try to focus on the concepts without worrying about the mathematical details. As a reminder, the matrix equation of linear regression is capital X, boldface beta, equals boldface y. That's equation 15.7. Capital X is the design matrix and therefore comprises known values. Boldface y, so vector y, is the observed data and therefore also comprises known values. Boldface beta, however, is a vector of unknowns. These are the coefficients or weights that tell us how to combine the regressors, so the columns in the design matrix, to get the closest fit to the data. The goal of model fitting is to obtain those beta values. You may be thinking that to solve for beta, we simply divide by x. Indeed, if these variables reflected individual numbers and not matrices, then the solution would be simple. Beta equals y divided by x. As a reminder, equation 15.7 was x times beta equals y. However, division is not a defined operation in linear algebra, so we need another technique. If X were a square matrix, we could use the matrix inverse to obtain beta equals inverse of X times Y. But X is almost never square. A square design matrix would mean having the same number of observations as predictors, which is a ridiculous constraint. Instead, the design matrix usually has more rows, so observations, than columns, regressors. A matrix with more rows than columns is called a tall matrix and does not have a full inverse. However, it has a left inverse, which allows us to cancel the x from the left-hand side of the equation, thereby isolating beta. Here we have a sequence of equations. I will read just the first one, which is 15.8, and that is capital X, so boldface X times boldface beta equals boldface Y. And then we have the final equation in the series, which is equation 15.10, and that is boldface beta equals the quantity X transpose X, that multiplication inverse, times X transpose times Y. Back to the text. If you are unfamiliar with linear algebra, then these equations probably look intimidating. The key concept is that we need to solve for the vector of unknown coefficients, beta, and the term X transpose X inverse times X transpose is called the left inverse and allows us to cancel the tall matrix. This operation is valid provided we apply the same multiplication to both sides of the equation. If you are familiar with linear algebra, then you will recognize that equation 15.10 is valid only if X is full column rank, which means that the regressors form an independent set. Dependencies in the design matrix lead to a situation called multicollinearity, which prevents an accurate solution. You'll see the consequences of multicollinearity in the exercises. Footnote. Another note for the linear algebra knowledgeable. The inverse is not actually used in the least squares implementation due to the risk of numerical instability. Instead, computers will implement more numerically stable algorithms such as QR or LU decompositions in combination with row reduction and Gaussian elimination. End footnote. Section 15.5.1 Predicted Data and Residuals. Capital X times boldface beta, the weighted combinations of the IZs, is called the predicted data or some variation like predicted values or model predictions. When do the model predictions exactly equal the observed data? Equation 15.8 has an exact solution only if the regressors can perfectly explain the data. That's almost never the case. In fact, it shouldn't be the case. The purpose of statistical modeling is to have a simplified model of reality, not a complete mathematical description of reality. Sampling variability, noise, and unexplained sources of variance will mean that the design matrix cannot perfectly predict the DV. And this, in turn, means that equation 15.8 is not a true equality. Instead, it is an approximation. The discrepancies between the model predictions and the observed data are captured by the variable epsilon. Therefore, the full GLM equation looks like this. Here we have equation 15.11, which reads boldface X boldface beta equals boldface Y plus boldface epsilon. You might see variations of equation 15.11, for example, setting y hat equals y plus epsilon, and then x beta equals y hat. The concept is the same. The weighted combination of regressors does not exactly equal the observed data, and the discrepancy between the predicted and observed values is indicated with variable epsilon and is called the residuals. This paragraph refers to figure 15.4, which is basically the same thing that I described in figure 15.1. It is a graphical view of regression. We see individual data points, so observations, in gray circles represented as gray circles, and then we see the best fit line as the predicted data, or that's the regression line. The predicted data, which is y hat, are the values that lie on the line with vertical projections to the observed data. And those projections, so the dashed line going from the predicted values to the observed values, those correspond to the epsilons or the residuals. Back to the text. The residuals are important. They are used to evaluate the overall fit of the model to the data and to diagnose potential problems with the data or the regression model. Section 15.5.2, Proof of the least squares equation. Equation 15.10 is the linear algebra solution to solving for beta, but it doesn't prove that the solution is the best solution. To show that the least squares solution gives the best possible set of beta coefficients, we can approach the regression problem from an optimization perspective. The goal is to get the predicted values as close as possible to the observed data values, which means to find the beta values that make epsilon as small as possible. Let's start by modifying the GLM equation. Here we have equation 15.12, which reads the magnitude of epsilon squared equals the magnitude of the term x beta minus y and all of that squared. The notation of something inside a double vertical line and then squared is called the squared vector norm and is computed as the sum of squared elements in the vector. Where does this come from and why do we care about it? Consider that we want the magnitudes of the residuals to be small. We don't care about their signs. Squaring the residuals makes them all positive, and summing them together gives us one number that reflects the overall magnitude of the residuals. Now for the optimization. The goal is to find the beta that minimizes the magnitude squared of the epsilons. In other words, find us the solution that gives the least squares. This can be mathematically expressed in equation 15.13, which reads argmin of beta and the magnitude of the quantity x beta minus y and all of that squared. If you've taken a calculus course, you will recognize the form and the solution to this optimization problem. We set the derivative to 0 and solve for beta. Here we have a series of 4 equations. I'm not going to read all of them out, but suffice it to say that we set the derivative of the minimization term to be 0, and then we solve for beta, and we wind up with equation 15.17, which reads beta equals the quantity x transpose x inverse times x transpose times y. If you are unfamiliar with matrix derivatives, then don't worry about understanding each of those equations. You do not need to grasp the calculus to understand or successfully apply regression models. The upshot is that we defined the objective function as the beta that minimizes the sum of squared residuals, and the result was the same as what we obtained from the linear algebra approach in equation 15.10. This proves that the left inverse method isn't just a solution, it's the best possible solution. Footnote. There are some mathematical details I've omitted here, for example, proving that the problem is convex and the solution is the minimum. That gets even deeper into the calculus of least squares, and while I encourage the math-savvy readers to satisfy their curiosity elsewhere, I don't want to get sidetracked into a pages-long proofs that are unrelated to the application and interpretation of regression. Section 15.6, Evaluating Regression Models. There are 3 ways to evaluate the statistical significance of a regression model. These are not mutually exclusive methods, but instead are used in combination to evaluate different aspects of the model. I will explain all 3 methods in detail, but first a brief overview. Method 1. Evaluate the entire model. Here you consider the model to be one statistical object, that is, without considering individual regressors, and evaluate whether the model provides a statistically significant fit to the data. The tests include an F-test and an adjusted R-squared. This test is done first because it doesn't make sense to evaluate components of a model when the model itself is terrible. Method 2. Compare quote-unquote nested models. Here you build 2 models, one of which is a subset of the other. For example, one regressor is removed. And compare which of the models provides a better fit of the data, accounting for the difference in the number of parameters. This approach allows you to evaluate whether the individual regressors or sets of regressors make significant contributions to the model. Method 3. Evaluate individual regressors. This involves evaluating the statistical significance of individual regressors using t-values. It is possible, for example, that the model is a statistically significant fit to the data, but some individual regressors are not statistically significant. Section 15.6.1, Overall Model Fit. Regression models vary in their complexity. There may be 2 or 200 regressors, with or without interactions. It is often relevant to know which predictors are statistically significant, their signs and magnitudes, etc. But it makes sense to interpret individual regressors only if the model is overall a reasonable fit to the data. Therefore, before testing and interpreting individual regressors, you check the model F-statistic and adjusted R-squared. Sum of squared terms. Evaluating the model fit to data relies on sum of squares terms. As you know from Chapter 14, the sum of squares, abbreviated SS, is conceptually comparable to variance in that it is the sum of squared differences between 2 sets of values, which is exactly the quantity we seek to minimize in a regression analysis. For evaluating regression models, there are 3 important SS terms. Those are listed in equations 15.18 through 15.20. We have the SS total. That is the sum over all values in the data set, so from I equals 1 to n, of the squared term y sub I minus y bar. That has df total of n minus 1, so n minus 1 degrees of freedom. And then we have equation 15.19, which reads the SS model is the sum of the squared differences between the predicted data value and the grand mean. So SS total was the observed data minus the mean, and SS model is the predicted data minus the mean. And finally, we have the SS epsilon, that's the equation 15.20, and that is the difference between the individual data points and the predicted data points, and it's that term squared. That has n minus k degrees of freedom. Back to the text. In words, SS total is the total variation in the dataset around its mean, and when divided by its df, this is the data variance. SS model is the total variation of the predicted data around the data mean, and SS epsilon is the total variation of the predicted data relative to the observed data. The intuition for the DF model, and that is k minus 1, so there are k minus 1 degrees of freedom for SS model. The intuition for the DF model is that although there are n predicted data values, each value is generated by combining k terms. Therefore, there are only k minus 1 factors that contribute to each data value. As for df sub epsilon, that is n minus k, the model reduces the variability of the residuals by removing any variability attributable to the k parameters. Indeed, in the trivial case of n parameters, the model would perfectly fit the data, in which case SS epsilon is trivially 0. These three sum of squared terms are related to each other, as in an ANOVA, in that the SS total is partitioned into the sum of two sources of variability: the explained variability that is attributable to the model, and the unexplained variability that is captured by the residual. That is illustrated in equation 15.21, which reads SS total equals SS model plus SS epsilon. The two methods for evaluating model fit, F and R squared, are based on comparing these SS terms. I hope you have the intuition that if the model is a good fit to the data, then SS model should be close to SS total, and SS epsilon should be relatively small. F statistic. The goal of the regression F-test is to evaluate the ratio of explained to unexplained variability. I hope this sounds familiar from the ANOVA F-test. In the case of regression, the F ratio is defined as follows. Here we have equation 15.22, which reads F with k minus 1 and n minus k degrees of freedom equals the ratio, where in the numerator we have SS model divided by k minus 1, and the denominator we have SS epsilon divided by n minus k. K is the number of parameters in the regression model, including the intercept term. Confusingly, some people define k as the number of parameters excluding the intercept term, which would mean that the degrees of freedom would be listed as k instead of k minus 1 and n minus the quantity k plus 1 instead of n minus k. There is nothing I can do about this inconsistency except promise to be consistent in this chapter about counting all parameters and not arbitrarily excluding the intercept. After all, there is nothing mathematically or statistically special about the intercept. Anyway, the intuition behind equation 15.22 is that the better the model fits the data, the smaller the SS epsilon term, which increases the F ratio. It is necessary to scale the SS terms by their degrees of freedom because the terms inflate simply by increasing the sample size and the number of parameters. Now, this inflation is not the same for both terms and therefore would not cancel in the fraction. Gratuitously adding more regressors to the model will decrease SS epsilon, even if the added regressors are meaningless. For example, including variables about the number of grapefruits eaten per year by the research participants. But that also increases k, and as k gets larger, the numerator shrinks while the denominator increases, which in turn decreases the F value. Therefore, adding more regressors to the model will actually make the model a worse fit to the data, unless those additional regressors account for a meaningful amount of variability. The take-home message is that you should add regressors to the model only if you can justify making the model more complicated. The F ratio is evaluated in the same way that you evaluate the F values in ANOVAs, by computing the probability of observing an F value at least as extreme, given the null hypothesis distribution associated with the numerator and denominator degrees of freedom. And if that p-value is less than 0.05, then you can consider the regression model to be a statistically significant fit to the data. Notice that this f-test does not directly involve evaluating, comparing, or interpreting the individual regressors in the model. Adjusted R-squared. Adjusted R-squared is a measure of the amount of variance in the DV that can be explained by the model. It has a maximum of 1, indicating that the model explains every single iota of variability in the data, and a value of 0 indicates that the model explains nothing interesting in the data. Now you might think that adjusted R-squared would be computed as the squared correlation coefficient between the predicted data and the observed data. That is a sensible thought. Such a squared correlation would range from 0 to 1, and larger correlations would indicate a closer match between the predicted and observed data. In fact, this quantity is referred to as R-squared without the adjustment. However, there are two problems with this approach. Problem 1, the correlation ignores mean offsets. For example, predicted data of 100, 101, 102 would correlate perfectly with observed data of 5, 6, 7, although the predictions are terrible. Problem 2, R-squared increases with any increase in model parameters, even if those parameters are unrelated to the DV because of overfitting. You'll demonstrate this empirically in exercise 2. Therefore, the formula to compute adjusted R-squared is presented in equation 15.23. This equation reads R-squared adjusted equals 1 minus the ratio of the sum of squared epsilon divided by the sum of squared total. And rewriting this out, that gives us 1 minus the ratio of the sum of all the squared differences between the observed data and the predicted data, compared to, in the denominator, we have the sum of all the squared differences between the observed data and the average of the data. In other words, adjusted R-squared is the ratio of the squared discrepancies of the predicted versus the observed data to the squared discrepancies of the observed data to its mean. In effect, this is a model comparison approach where the quote-unquote baseline model in the denominator states that the data simply equal their mean. As the model predicted data get closer to the observed data, the numerator goes to 0, which means that the adjusted R-squared will approach 1. It is mathematically possible to have an adjusted R-squared of less than 1, which would indicate that the model is actually doing worse than just predicting the average value. If that's the case, then there is something horribly wrong with the model. Adjusted R-squared is qualitatively interpreted metric. There is no associated p-value or threshold for statistical significance. You will need to compare your adjusted R-squared value to other results in your field. Section 15.6.2, Comparing Nested Models. Consider the following two equations. Here we have two equations. Equation 15.24 reads m sub 1 for model 1. Y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x1 times x2 plus epsilon. Then we have equation 15.25. This is for model 2, so m sub 2. And that equation is exactly the same as 15.24, except the interaction term is dropped. So the beta 3 times x1 times x2, that term is dropped from equation 15.25. Model M2 is quote-unquote nested under model M1 because both models have the same DV and the same regressors, except that M2 is missing one regressor. Model M1 is also called the full or extended model, and M2 is called the reduced or nested model. The goal of comparing these two models is to evaluate whether the interaction term provides a statistically significant benefit to the model, as quantified by the amount of reduction in the SS epsilon term. But here's the thing. Any model with more parameters is basically guaranteed to fit the data better. Even a regressor comprising random numbers is likely to correlate with the DV at least a little bit, purely by chance. So it is trivial that model M1 will fit the data better than model M2. More generally, the full model will always explain more variability than the reduced model. This is why we need to penalize the full model for having more parameters. The two models are compared using an f-test, and this is shown in equation 15.26, which reads f with p minus k and n minus p minus 1 degrees of freedom equals the ratio of, in the numerator, we have the quantity of SS epsilon reduced minus epsilon SS epsilon full, and that difference is scaled by p minus k. And then in the denominator, we have SS epsilon for the full model divided by the quantity n minus p minus 1. So SS epsilon r is from the reduced model or the nested model. SS epsilon f is from the full model or the extended model. P is the number of parameters in the full model. K is the number of parameters in the reduced model. And n is the total sample size. Again, P and K refer to the total number of parameters, including the intercept, thus corresponding to the number of columns in the design matrix. As I wrote above, the full model will always explain more variability than the nested model, so the numerator of the F statistic will be positive. Recall that a smaller SS epsilon corresponds to a better fit to the data. The question is whether it is large enough to overpower the penalty term introduced by the larger DF term in the denominator. As a conceptual analogy, if you remove the normalization terms p minus k and n minus p minus 1, then the ratio is actually the proportional increase in unexplained variability in the reduced compared to the full model. Therefore, this F value quantifies how much worse the reduced model is compared to the full model. If the F value is statistically significant, it means that more regressors improves the model, and so you should prefer the more complicated model. On the other hand, if the F value is not statistically significant, it means that the two models fit the data roughly equally well, and so you should prefer the simpler model. Thus, a significant result means to use the full model, a non-significant result means to use the reduced model. The examples shown in this section, so M1 and M2, involved a nested full model pair that differed only by one parameter, that was beta 3. Having two models differ by one regressor does facilitate a clean interpretation, because a statistically significant F value can be attributable to exactly one parameter. On the other hand, there may be experimental or theoretical motivations for dropping several related terms in the nested model. For example, imagine a study on predicting home sale prices based on many regressors that are grouped into those related to the physical attributes like total size, the number of bathrooms, the years since original construction, national economic attributes like inflation, bank loan interest rates, stock market growth over the past year, and buyer attributes, for example, age, number of children, and annual income. You might want to compare nested models that exclude all regressors from one group. Section 15.6.3, Evaluating Individual Regressors. The regression F statistic does not break down the contribution of each individual regressor. Instead, it merely tests whether the model as a whole is a statistically significant fit to the data. Now, there are applications in predictive modeling where the individual regressors are not of interest, but in most cases, people perform a regression analysis because they want to evaluate and interpret individual regressors. This is not trivial because it is possible for the regression model overall to be significant, while some individual regressors are non-significant. Individual regressors are evaluated using a t-value, where the null hypothesis is that the coefficient is not different from 0. In other words, h0 is beta equals 0. The t-value is conceptually the same as you learned in chapter 11, so a ratio of the mean effect to its standard error, that's SE in the equation below. The t-value associated with the jth regressor is as follows. So here we have three equations. Equation 15.27 reads t with n minus k degrees of freedom is beta sub j, so the jth beta term, divided by SE, the standard error of that beta term. Then I define the standard error of beta sub j in equation 15.28, and that is the square root of the fraction we have in the numerator ms, the mean squared epsilon, and in the denominator we have the inverse of the matrix product x transpose x, and then the j comma j element in that inverse. I'll discuss this in a moment. And then finally, I define ms sub epsilon in equation 15.29, and that is simply the ss epsilon term divided by df epsilon. A few notes about these equations. Note 1. The inverse of the matrix x transpose x may look confusing if you are not comfortable with linear algebra. It is the element in the jth diagonal of the inverse of the gram matrix of the design matrix. This term was also used in the least squares equation. I know that's quite a mouthful, but it's essentially a combination of the variance of the jth regressor and its covariance with the other independent variables. Note 2. The standard error is proportional to the fraction of the total data variability that cannot be explained by the entire model. Note 3. The t-value and the ss epsilon term have the same degrees of freedom. Thus, the statistical significance of one coefficient depends in part on the other coefficients in the model. After obtaining the t-value, its statistical significance is computed using the same t-PDF that you used to evaluate the t-value in a t-test. As I wrote earlier in this chapter, the intercept term is necessary, but is often uninterpretable. For example, it prevents predicted life happiness from plummeting to 0 simply because no ice cream was consumed. So don't get too excited about a statistically significant intercept term. Non-significant f. If the model f ratio is not statistically significant, then it is inappropriate to evaluate individual regressors. Indeed, in theory, there should not be significant regressors with a non-significant model. However, it is possible to have an f-test with p greater than 0.05, while some regressors have p less than 0.05. This is likely a type 1 error due to noise, low sample size, or violations of the assumptions of regression. You should not interpret a p less than 0.05 regressor in a model that is a non-significant fit to the data. No significant regressors. It is possible that the model has an f-test with p less than 0.05, while all regressors have p greater than 0.05. This is an awkward situation because it means that the model is significant overall, while no individual regressor can be interpreted as having made a significant contribution. As with the previous scenario, this situation is likely due to small effect sizes, considerable variability, or low statistical power. It is also possible that there are problems with the regression model, such as multicollinearity, meaning the IVs are too strongly correlated with each other, causing numerical estimation problems. Either way, if you encounter this situation, interpret the results cautiously and consider whether the dataset can be improved by cleaning or increasing the sample size. Section 15.7, Standardizing Regression Coefficients. First, a note on notation. When writing about regression generally, the coefficients are indicated using beta, the Greek letter beta, which helps separate them visually from their associated IVs. For example, a regression model about the impact of blood loss on surgical outcomes might have a term beta sub 1b, where B is for blood loss volume. But in discussions of standardization, B is used to indicate unstandardized coefficients, while beta is used to indicate standardized coefficients. I dislike this notation because the blood loss regression term would be B sub 1b. In my humble opinion, a much better notation would be beta sub z.1 to indicate the standardized beta sub 1. I will use this notation here in the interest of legibility. As I've already discussed, the beta coefficients have no units. They are simply numbers that encode the change in the dV per unit change in the IV to which that beta is attached. But they are often interpreted in terms of their units of their associated regressor. In some cases, having units in the scale of the data is ideal because it facilitates interpretation. For example, in long-term financial planning, it is useful to know that for each additional $100 contribution to a diversified stock market index fund at age 20, you can expect an additional $200 per month at age 60. Footnote: that calculation is based on a super rough approximation. Please don't use this example as financial advice, although you should follow this advice. If you are not already planning for your financial future, start now. Back to the text. There are 4 limitations of the quote-unquote raw coefficients that motivate using standardized coefficients. First, the units in the regression model can be confusing. Consider that when regressing age on height, the numerical value of the beta will change drastically depending on whether height is measured in centimeters, inches, feet, or light years. And the beta coefficients from interaction terms usually have bizarre and uninterpretable units. For example, sleep hours by study hours in a study on the impact of sleep and study time on exam performance. Second, many transformations render the data into units that are completely uninterpretable. This is especially the case when nonlinear transformations or a sequence of transformations is applied. Third, unstandardized coefficients are difficult to compare across terms if the units or scales are different. For example, imagine a study measuring the impact of calories consumed and minutes of moderate exercise on weight loss. It is simply impossible to compare beta sub calorie to beta sub minute because their units and their numerical scales are different. Fourth, numerical computational issues can arise if the numerical scales of different variables differ by orders of magnitude. For example, imagine you are trying to predict someone's retirement savings measured in cents based on their magnetic brain activity measured in Teslas. Those two measurements can be 20 orders of magnitude apart, and modern computers will run into numerical precision problems during the calculations. You'll see a less extreme version of this issue in real data in exercise 11. An alternative is to standardize the regression coefficients. Standardized betas have units of standard deviation, hence the notation beta sub z, which is great because anyone with minimal statistics education will be able to interpret the results. The interpretation then becomes the standard deviation change in the dV for each standard deviation change in the IV. Going back to the calories weight example above, we might find that the standardized coefficients for calories and minutes are 0.5 and minus 0.07, which would indicate that for each additional standard deviation of calories consumed, weight loss increases by 1/2 of a standard deviation, whereas for each standard deviation increase in exercise duration, weight decreases by 0.07 standard deviations. Those standardized coefficients are directly numerically comparable. Section 15.7.1, two methods to standardize coefficients. The first method is to normalize the quote-unquote raw or unstandardized beta values. Here we have equation 15.13, which reads beta sub z dot k equals beta sub k times the ratio of, in the numerator we have s sub x sub k, and in the denominator we have s sub y, where s is the standard deviation, x sub k is the kth term in the design matrix, and s sub y is the standard deviation of the dV. Notice that the standardization is based on the standard deviations of the IV and the dV. That is necessary because the interpretation of the standardized coefficients is, quote, the standardized deviation change in y resulting from one standard deviation change in x, unquote. The second method is to consider what would happen in equation 15.30 if the data were already standardized. That is, if s sub xk equals s sub y equals 1. In that case, beta sub z point k equals beta sub k. Thus, the second method to standardize the regression coefficients is to standardize all of the variables before running the regression model. You need to standardize all of the data, the dV, and all columns in the design matrix. How about the intercept term? Does that need to be standardized? Well, the intercept is a column of all ones, and so its standard deviation is 0. Therefore, s sub x0 equals 0, which means beta sub z.0 equals 0. So the standardized intercept term is trivially 0. And this should make sense. The intercept is interpreted as the value of the dV when all IVs are set to 0. If all data are standardized, then all data are mean-centered. And this is why a standardized dataset is the one exception where the design matrix does not need an intercept term. You will have the opportunity to implement both of these methods in exercise 12. Section 15.7.2, when to standardize. Both beta and beta sub z are useful, but they serve different purposes and are advantageous in different situations. When to leave the coefficients unstandardized. There are 3 situations that motivate unstandardized coefficients. Situation 1, you want to interpret the regression model in the same units as the data. Situation 2, you will use the regression model to predict new data that are unstandardized. This is a common application in machine learning and predictive analytics. Situation 3, you only want to interpret the statistical significance and sign of the regression coefficients. When to standardize the coefficients. There are 4 situations that motivate standardized coefficients. Situation 1, you want to compare across predictors that have different scales and/or units. For example, the impact of calories versus exercise minutes on weight change. Situation 2, data transformations make the numerical values of the beta confusing or uninterpretable. Situation 3. You or your audience find standard deviation units more comfortable to interpret. Situation 4. As a measure of effect size. It is not straightforward to measure the effect size of individual regressors due to shared variance between IVs, and so standardized coefficients are used to interpret the importance of each regressor for the DV. Section 15.8, Regression in Python. There are several ways to build and evaluate a regression model in Python. You can directly implement the least squares math. This is good to do once, for example, in exercise 1. But in practice, you should use dedicated libraries that implement more numerically stable algorithms for solving the least squares problem and that provide additional results, including p-values and diagnostic tests. I will focus on using a method called OLS that comes with the stats models library and is often abbreviated as SM. OLS stands for ordinary least squares and implements the equations I showed earlier. I will provide several examples of regression models later in this chapter. The text below provides a summary of the procedure. The first step of using sm.ols is to create a design matrix in which the columns correspond to IVs and the rows correspond to observations. You can create the design matrix as a NumPy array or a pandas data frame. I'll show both approaches. You can explicitly include an intercept term in your design matrix, or you can use a function provided by SM to add an intercept term to the matrix or data frame. I prefer to add my own intercept term, but this is a matter of personal preference. The second step is to fit the model. This involves calling the sm.ols function with inputs indicating the DV and design matrix and calling the fit method on that object. The code is organized as follows, where variable y is a vector of DV values and variable x is the design matrix. For reasons I cannot fathom, SM calls the DV endog for endogenous and the design matrix exog for exogenous. Here is a line of Python code. We see variable output reg results, regression results equals sm.ols with two inputs, endog equals y and exog equals x dot fit. Make sure the design matrix is oriented with regressors in the columns. If the matrix is transposed, that is, the regressors in the rows and observations in the columns, the function will crash and you'll get an error message about endog and exog matrices are different sizes. The third step is to inspect the summary table of the regression model, which I will detail in the next section. The fourth step is to visualize the results of the regression. There are myriad ways to visualize the results of a regression analysis, and I will show many examples in the next sections and in the exercises. Broadly speaking, there are 4 features of a regression that you can plot. First, we have the data. Because data for regression models are continuous, scatter plots are suitable. For a simple regression, this is straightforward, while a multiple regression requires some creativity to visualize. Look for linear relationships, outliers, and distribution shapes. If there are visually obvious nonlinear relationships, you may consider applying data transformations or using a nonlinear modeling approach. The predicted data. The model predictions, that is y hat, should match reasonably well to the observed data, though they will have less variability. The residuals. The residuals, that is epsilon equals y hat minus y, should be uncorrelated with the predicted data and should be normally distributed. Therefore, scatter plots of the residuals against the predicted data and histograms of the residuals are often visualized. Coefficients. The beta coefficients can be reported in the text, displayed in a table, or visualized in a bar plot with error bars indicating the 95% confidence intervals. Not all of these visualizations are necessary to show in a publication or formal presentation of the data. Indeed, detailed visualizations of regression model outputs may confuse people who are unfamiliar with statistics, but these visualizations should be used by you and your statistics knowledgeable collaborators to inspect and evaluate the regression model performance. Section 15.8.1 Interpreting the output of SM.OLS. SM.OLS provides a table of regression outputs, an example of which you can see in Figure 15.5. This table shows results of a simple regression with an intercept and one regressor called age, and is taken from a simulated dataset that I'll introduce in the next section. Each of the numerical values in the table can be extracted from the output of sm.ols.fit, as you will discover in the exercises. This paragraph refers to Figure 15.5, which shows an example output of a regression model from sm.ols. The figure illustrates a table with 3 sections, so different multiple rows in each section, and the sections are separated by rows of equal signs. Now, you really need to look at the text to appreciate this figure because it's really just a bunch of text. There's nothing interesting visually that I can describe about this. Back to the text. There are many metrics provided in the output table. Some of them are obvious. For example, deep variable is the name of the dependent variable. Below, I will describe some of the metrics you should inspect. I'll break this down by the 3 subtables separated by rows of equal signs. First, we have the top subtable that corresponds to overall model information. This provides basic information about the model, including the model type, so OLS, least squares, the degrees of freedom, R squared and F statistics, and so on. AIC and BIC stand for Akaika Information Criterion and Bayes Information Criterion. These are used for comparing nested models and polynomial regression models, and I will discuss them later. Next, we have the middle subtable for individual regressor statistical significances. This table contains the inferential statistical tests of individual regressors. Each row corresponds to a regressor. Coef is the value of the beta coefficient. STD error is the standard error. And you can easily confirm that that the t-value is the beta divided by its corresponding standard error. The corresponding t and p values are provided, and the 0.025 and 0.975 columns list the bounds of the 95% confidence interval around the beta parameter. Finally, we have the bottom subtable, which corresponds to diagnostic tests. This section provides a list of diagnostic statistics about the data and the model. Omnibus, and its associated prob value, is the result of an omnibus test on the residuals to evaluate their normality. As a reminder, p greater than 0.05 is a good thing because it suggests that the residuals are normally distributed. The Durbin-Watson test evaluates autocorrelations in the residuals. The value ranges from 0 to 4, with a value of 2 indicating no autocorrelation. Values less than 1 or greater than 3 suggest the presence of autocorrelations in the residuals, which could be problematic for the model evaluation. Skew and kurtosis refer to the data distribution characteristic. As you know from Chapter 4, the skew and kurtosis of a Gaussian are 0 and 3. The Jarku-Berra test evaluates these metrics together and p greater than 0.05 suggests that the data were drawn from a normal distribution. Cond no is the condition number of the design matrix. In the context of GLMs, the condition number reflects the sensitivity of the model to small perturbations. Imagine, for example, that the beta coefficients fluctuated wildly if you added one more data observation, or if there were a bit of noise in the measurements. Such a model is highly sensitive to small changes in the design matrix and provides untrustworthy results. There are no specific cutoffs for a quote-unquote good condition number, but large values can indicate the presence of multicollinearity. Smaller is better, and the smallest possible condition number is 1. SM.OLS will issue a warning in the case of a high condition number. You'll see an example in exercise 11. Other Python libraries for regression. There are several Python libraries that provide functions for implementing regressions. As you'll see in exercise 1, you can implement the basic least squares equation using NumPy, although it would be a lot of additional work to code the rest of the output provided by sm.ols. Another option is the linear regression method in the scikit-learn library. This method is optimized for prediction accuracy in machine learning tasks and does not provide as many additional checks and diagnostics as sm.ols does. Reproducing regression results using linear regression is the purpose of exercise 5. Regression models can also be computed in TensorFlow and PyTorch, although these libraries are optimized for nonlinear learning, such as deep neural networks. The point of this paragraph is that if your goal is to obtain detailed statistical and diagnostic information about a regression analysis, then sm.ols is the best approach. Section 15.9, Regression in R. There are several R functions with which to build and evaluate regressions in R. I will focus on the LM function, where LM stands for linear model, because it is versatile and commonly used. For more complex models, you might also use LME. For educational purposes, I recommend computing a regression by directly implementing the math. That's in exercise 1, but in practice, it's better to use dedicated functions that implement more numerically stable algorithms. The first step of using LM is to define the regression formula. That formula looks vaguely reminiscent of the mathematical model of regression shown in equation 15.1. That's y equals beta 0 plus beta 1 x1 and so on. Although you don't specify all of the terms. For example, below is a regression model equation and its translation into R. Here we have equation 15.31, which reads y equals beta sub 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 times the quantity x1 times x2, so the interaction between x1 and x2, plus epsilon. And then below that equation, I have some code which reads variable formula equals y tilde, it's like the little squiggly character, y tilde x1 plus x2 plus x1 colon x2. The variable formula uses the tilde character to indicate that the dv on the left is predicted from the IVs on the right. Also notice the colon notation for the interaction term. If you want to include all main effects and interactions, you can use an asterisk to expand all terms. For example, the following two formulas would produce identical models. Here we have 2 lines of code. The first line is variable formula 1 equals y tilde x1 plus x2 plus x1 colon x2. And the next line of code reads formula 2 equals y1 tilde x1 asterisk x2. The variables y, x1, and x2 correspond to column names in the data frame that contains the DV and the IVs in columns. This data frame needs to be in wide format, so if your data are stored in long format, you'll need to use the melt function to transform the data frame. If you want to build a full model that includes all IVs and all possible interactions based on all columns in the data frame, you can use the following shortcut. Here we have a line of code that reads formula equals y tilde period. The period, or dot, indicates that all columns in the data frame except for the one labeled y should be included. Notice that the R formula does not explicitly include the beta terms, nor does it include the intercept or epsilon. Okay, the second step is to fit the model. This involves inputting the formula and the data frame into the LM function. Here we have a line of code MDL for model equals LM with two inputs. The inputs are formula and DF. The output of the LM function is an object that contains useful information about the regression results. As a reminder, the variables in variable formula must correspond exactly to the column names in the data frame DF. Any differences in spelling or capitalization will produce errors. The third step is to inspect the summary table of the regression model. I will write more about this in the next subsection. The fourth step is to visualize the results of the regression. There are myriad ways to visualize the results of a regression analysis, and I will show many examples in the next sections and exercises. Broadly speaking, there are 4 features of a regression that you can plot. Feature 1 is the data. Because the data for regression models are continuous, scatter plots are suitable. For a simple regression, this is straightforward, while a multiple regression requires some creativity to visualize. Look for linear relationships, outliers, and distribution shapes. If there are visually obvious nonlinear relationships, you may consider applying data transformations or using a nonlinear modeling approach. Feature 2, the predicted data. The model predictions, so y hat, should match reasonably well to the observed data, though will have less variability. Feature 3, the residuals. The residuals, so epsilon equals y hat minus y, should be uncorrelated with the predicted data and should be normally distributed. Therefore, scatter plots of the residuals against the predicted data and histograms of the residuals are often visualized. Feature 4, coefficients. The beta coefficients can be reported in the text, displayed in a table, or visualized in a bar plot with error bars indicating the 95% confidence intervals. Not all of these visualizations are necessary to show in a publication or formal presentation of the data. Indeed, detailed visualizations of regression model outputs may confuse people who are unfamiliar with statistics, but these visualizations should be used by you and your statistics knowledgeable collaborators to inspect and evaluate the regression model performance. Section 15.9.1, Interpreting the Output of LM. The text below shows R code implementing a regression model of age on height. This corresponds to an example that I will introduce in the next section. Here we have 2 lines of code. First line is model equals LM. The first input is height tilde age. The second input is data equals DF, where DF corresponds to the variable name of the data frame. The second line of code reads summary and input model. Okay, and then we have the output, that is the call, is LM. This is just repeating the line that I just stated, the LM line. And then we have a table for residuals. We have a table for coefficients. And then we have significances and some other information like the standard error, multiple R-squared, and F-statistic. The summary has the following sections. So there's a section for call. This is simply an echo of the code line. It may seem redundant if you run only one regression at a time, but it is useful if you have multiple models and inspect them later on in the code or save them to disk and share with others. Residuals. This lists descriptive statistics of the model residuals. Because the residuals should be random and Gaussian distributed, these characteristics should be roughly symmetric. That is, the minimum and maximum should be roughly the same magnitude with opposite signs, same for quartiles 1 and 3, and the median should be close to 0. In small samples, there might be notable asymmetries, as in the example above. Coefficients. This table shows key inferential statistics of the model with one row for each term in the model. The estimate row is the unstandardized beta value, and you can quickly confirm that the estimate divided by its standard error is the t-value. The number of asterisks to the right of the p-value helps you quickly determine statistical significance. Final 3 rows. This text provides overall information about the statistical significance of the regression model. There are other features of a regression model that you can obtain using different calls to the MDL variable object. For example, tidy MDL. This is in the Broom library. This provides only a table of coefficients. Glance MDL, also in the Broom library. This provides additional information about the entire regression model, including the Akaika information criterion and Bayes information criterion. These are used for comparing nested models and polynomial regression models, and I will discuss them later in the chapter. Augment MDL, also in the Broom library. This function returns a data frame that contains the data used in the model, plus additional columns for the residuals, raw and standardized, predicted values, and estimates of leverage and influence of each data value on the beta estimates. Check_model MDL. This is in the performance library. This function provides highly detailed information about the data, the model, and the residuals that might be useful for rigorous inspection. Other are functions for regression. There are several ways to implement a regression in R. In this chapter, I focus on LM in the interest of consistency and because it is a commonly used function. If you have sophisticated or unusual designs, you may find that using a different function or collection of functions will be more useful. Other R functions to implement regression models include GLM, LME-R, NLME, GAM, and robust base. It would take at least an entire separate chapter to discuss these regression variations in detail. But the good news is that all regressions are based on common mathematics and interpretations that you are learning about in this chapter. Section 15.10, Simulating Data for Regression. Simulating data to explore concepts and code in regression is straightforward. Start with the model equation, specify values for the beta coefficients and IZs, choose simulation parameters such as sample size and amount of noise, and then implement that model equation. As I discussed in Chapter 5, there are several advantages of simulating data to study regression, including generating data from models helps you understand how to construct models of real data. Creating datasets allows you to practice and explore analysis code and visualization methods without spending hours finding and importing datasets. And simulating data provides a ground truth that you can use to evaluate the accuracy of regression analyses while manipulating factors such as effect size, variable scaling, sample size, and noise characteristics. In this section, I will show 3 examples of simulating data for a regression analysis. I hope you will view these examples as starting points and inspiration for your own investigations, not as an exhaustive list of limited possibilities. Section 15.10.1, Example 1, one continuous regressor. Let's start with a simple example, predicting height based on age. Height is, of course, a nonlinear function of age, but for simplicity, I will approximate it as a linear function between birth and age 20. The model equation is as follows. Here we have equation 15.32, which reads h sub I equals beta sub 0 plus beta sub 1 a sub I plus epsilon sub I. H indicates height in centimeters, A indicates age in years, and the subscript I indicates child I. Notice that the beta terms have no I subscript. The same model coefficients are used for all children regardless of their age. Obviously, height is not entirely determined by age. There are myriad genetic and environmental factors that determine someone's height, and this unique and unaccounted variability is absorbed into the epsilon sub I term. Margin note: an equation that produces simulated data is also known as a forward model. Back to the text. Now we can define values for beta 0 and beta 1. Remember that the intercept term, so beta 0, is the expected height when a equals 0, which means at birth. The internet claims that 50 centimeters is a reasonable average. Beta 1 is the slope of the age variable. How many centimeters do we expect a child to grow for each year after birth? Well, the true function is nonlinear even before age 20, but let's use beta 1 equals 6 centimeters. In other words, we model height as increasing by 6 centimeters per year, starting at 50 centimeters. The next step is to pick a sample size and noise characteristics. I'll use n equals 135 and random noise drawn from a normal distribution with a mean of 0 and a variance of 15 squared. Keep in mind that in real data, the epsilon term is unexplained variability, which includes a mixture of true noise, so the measurement is inaccurate because the baby wiggled while being measured, and variability that is in principle explainable, but is not captured by the IVs. So genetics, for which we could use the parent's height as an index, sex, hormones, nutritional health, activity level, and so on. Then we generate a value of A for each member of our simulated population. To get an even distribution of all ages, I generated A as uniformly distributed random numbers between 0 and 20. Finally, we put all of this into code. First, I'll show the Python code. Here we have Python code. There are variables for the coefficients. So we have B0 equals 50, that's the intercept. B1 equals 6, that is the age slope. Then we have the parameters and variables. So I define variable n equals 135. Variable age equals numpy.random.uniform 0, 20, n. And then variable noise equals numpy.random.normal 0, 15, n. And then we generate the data, that is variable height equals B0 plus B1 times age plus noise. So that was the Python code. The R code looks nearly identical, except that the uniform distribution is created with a function RUnif, and the normal distribution data is created using a function RNorm. Back to the text. And voila, we have our data. Notice how the simulation works compared to a real regression analysis. In a real regression analysis, we have the data and we want to estimate the beta coefficients. In simulated data, we define the beta coefficients and then produce data. Now we can subject the simulated data to a regression analysis and compare the concordance between the betas from the analysis and those we used in the simulation, that is, the ground truth values. This paragraph references figure 15.6, which shows a scatter plot of simulated data of height by age. The x-axis shows age from 0 to 20 in years, and the y-axis shows height in centimeters ranging from around 35 or so to 180. And the relationship is clearly linear, increasing height with age, and there's a bit of noise to it. Back to the text. Running the regression analysis. Implementing a regression model is quite different in Python versus R. I'll explain the procedure first in Python and then in R. In Python, we need to organize the IVs into a design matrix. You can also create a list of vector names to print in the model summary. Here we have 2 lines of Python code. First line is variable design matrix equals numpy.vstack with a tuple as the input, and that contains numpy.ones n, age. And then that whole vstack expression is transposed with .t. And then I have another list that I define called IV names, which has intercept and age as the 2 elements. Now you can fit the sm.ols model and then print the summary table. Notice the optional inputs in the summary function. Without these, the dv is called y and the IVs are called x1, x2, and so on. Here we have 2 more lines of code. Reg results equals sm.ols, and we have input ndodge equals height and xodge equals design matrix, and then we call a method on the sm.ols object .fit at the end. And then the second line, I'm printing out the results with the command regresults.summary with input xname equals IV names and yname equals height. The summary table was shown in figure 15.5. This is the figure that I described earlier when discussing how to interpret the outputs of the sm.ols regression function. For now, you can check that the intercept, beta 0, is 52.35, which is very close to the ground truth value of 50, and that the age slope, beta 1, is 5.79, which is close to the ground truth value of 6. The discrepancies are due to the random noise added to the model, and you will explore in the exercises how noise affects the accuracy of those estimates. In R, we put the DV and IVs into a wide format data frame, then define the regression model and evaluate it using LM. Here we have 3 lines of R code. First line is df equals data.frame with inputs age and height. And then variable reg results equals LM with inputs height tilde age. And then data equals df. And the final line of code is summary reg results. Now for some visualizations. Figure 15.7 shows 4 visualizations of the regression model. Panel A shows the data in dark gray triangles. In real data, you should check for outliers or nonlinear relationships. The white squares show the model predicted data. These should follow the key trends in the data without the variability. It is uncommon to show the individual predicted data points because they all necessarily lie on the best fit line. I show them here as a reminder that the predictions are a reduced dimensional representation of the data that is based on the assumption that the discrepancies between the observed and predicted data are noise and can be minimized and ignored. This paragraph references figure 15.7. Figure 15.7 shows several visualizations of the data, predicted values, and residuals. There are 4 panels in this figure arranged in a 2x2 grid. First, I'll just describe panel A because that's what the paragraph of text just referred to. We have a scatter plot with age on the x-axis and height on the y-axis. And then there are dark gray triangles corresponding to the observed data, and white squares corresponding to the predicted data. All of the predicted data, so all the white squares, lie on the best fit line, but they follow the key linear trend in the observed data. Back to the text. Panel B shows a scatter plot of the observed versus predicted data. This model was wildly significant to p less than 10 to the minus 54. So it's not surprising that the correlation between y and y hat is so strong. There should be a linear relationship between these two variables, and there should be roughly the same variability across the entire range of the dV. Nonlinear relationships, or heteroskedasticity, indicate violations of assumptions and suggest that the model results may be poor indicators of the true relationships in the data. This paragraph references Panel B of Figure 15.7. Panel B shows the observed versus the predicted data in a scatter plot with the observed height on the x-axis and predicted height, so y hat, on the y-axis. They show a very strong linear relationship with a correlation coefficient of 0.94. Margin note. The R value that I just described is the unsquared raw R squared that I warned you not to trust. It is still informative with the visualization, but should not be used as a reliable quantitative indicator of model fit. You will see why in exercise 2. Back to the text. Panels C and D show features of the residuals. The scatter plot of the residuals by the predicted data in panel C should look like an unstructured cloud of random dots, and the correlation between the two variables should be 0. In fact, the correlation must be 0, but poor model fits will produce non-zero correlations in parts of the data. You'll see this in the next example. Finally, the distribution of the residuals in panel D should be Gaussian. Don't stress about this histogram being a perfect Gaussian, as long as it is roughly normal looking. The omnibus test in the summary output table will provide quantitative information on the distribution of the residuals. This paragraph refers to panels C and D of Figure 15.7. Panel C shows the residuals plotted as a function of the predicted height. And the correlation is R equals 0.00, and we see it just looks like a random cloud of noise. There's no obvious structure in this scatter plot. Panel D shows the distribution of residuals. So we have residuals on the x-axis, and it's a histogram which looks roughly Gaussian, although there is a bar that's a little bit unexpectedly high. That's a bit to the left of the center of the distribution. Section 15.10.2, Example 2, one continuous, one categorical IV. Do you prefer carrots or chocolate? Let's imagine an experiment where a research participant responds using mouse clicks to pictures of carrots and chocolate. We vary the brightness of the pictures and measure their reaction time. That is, the time delay between when the picture was presented and when they clicked the mouse button. This is the DV. For 50 different pictures of each food category. Visualizing multiple regression data can be difficult. One approach is to split the data on one of the variables. Fortunately, this is easy to do if one variable is categorical. Therefore, the simulated data are shown in Figure 15.8 with different marker shapes and colors used for different food categories. This paragraph references Figure 15.8, which shows the data for the regression simulation 2. On the x-axis, we have picture brightness as a % of maximum, and reaction time on the y-axis ranging from around 200 to around 700. So the scatter plot shows two groups. We have light gray circles for carrots and dark gray squares for chocolate. And what we see is negative relationships in both cases, both categories. So as picture brightness increases, the reaction time decreases, meaning that the Research participants in our fake experiment were faster to respond when the brightness was higher. And from visual inspection, it appears to be the case that this decrease is stronger for chocolate compared to carrots. Back to the text. Clearly, there is a decrease in reaction time with increased brightness for both categories of food. We don't need statistics to see that that's a real effect. Although a regression analysis would reveal the beta parameter, which encodes how much faster the reaction is for each unit increase in picture brightness. It also seems like the reaction to carrots might be slower than the reaction to chocolate. That is less visibly obvious, at least for brightness values below 60%. Indeed, it looks like there is an interaction between the two variables, such that the difference between response times to carrots versus chocolates is larger when the picture is brighter. Here is the model I used to simulate the data. Here we have a sequence of equations and definitions. Equation 15.33 reads R equals beta 0 plus beta 1b plus beta 2c plus beta 3b times c plus epsilon. And then I define below that beta 0 equals 600, beta 1 equals minus 2, beta 2 equals 60, beta 3 equals minus 2.5, and epsilon is drawn from a normal distribution with a mean of 0 and a variance of 50 squared. Back to the text. R is reaction time in milliseconds, B is image brightness, and C is the category, carrot versus chocolate, dummy coded to 0 and 1. Recall from the beginning of this chapter that the beta coefficients are formally unitless scalars, but that we can colloquially speak of the coefficients as having the units of their associated variables. In this example, the units of beta 0 are milliseconds. The units of beta 1 are milliseconds per brightness percent. That is, for each additional percent increase in brightness, the reaction time decreases by 2 milliseconds. And the units of beta 2 are milliseconds per category. Thus, pictures of carrots lead to a 60 millisecond increase in reaction time. The units of beta 3 are difficult to interpret. They are the products of the units of the individual variables, which in this example are milliseconds per brightness per category. But category doesn't have units. It's dummy-coded variable that is arbitrarily mapped onto 0 and 1 for carrots and chocolate. I could have assigned carrots equals 934.2 and chocolate equals 45. With values of 0 and 1, it doesn't make sense to describe chocolate as being 1 unit larger than carrots. Therefore, when 1 IV is categorical, the interaction term is interpreted more generally. It describes how the effect of brightness on reaction time depends on the food category. Building and evaluating the model. To introduce slightly different coding approaches, here I created the design matrix as a pandas data frame without an intercept, and then used the SM library to add the intercept. So here's some Python code. First, I construct the design matrix as a data frame. So I have variable df equals pd for pandas dot data frame, and then there's a dictionary where the first item or the first pair is brightness brightness, and then label category is variable category. Then I add a constant by specifying variable x equals sm.addConstant with input df. And then I fit the model by specifying variable model equals sm.ols with two inputs, rt and x, and then .fit. The R code is more compact than the corresponding Python code because we can specify the formula directly in the lm function. So here I have the variable model equals lm, and the first input specifies the design, so rt tilde brightness plus category, and the second input is data.frame df, rt. I won't paste in the entire model summary, although you can peruse it from running the online code. But here are the betas. Beta 0 equals 686, beta 1 equals minus 3.5, beta 2 equals minus 71.3. I'll get back to those values in a moment. Because the Seaborn Data Visualization Library is designed to work with Pandas data frames, I used Seaborn to create the visualizations in Figure 15.9. Notice that the predicted data and residuals are plotted using separate grayscale values for the categorical factor. This paragraph references Figure 15.9. Figure 15.9 shows several visualizations of the data, predicted values, and residuals. There are 3 panels organized in a single row. In panel A, to the left, we have the brightness on the x-axis and predicted RT on the y-axis. And then we have black circles for chocolate and light gray circles for carrots, and lines corresponding to the best fit lines. Now, these two best fit lines appear to be parallel, both going down. Then we have in panel B the residuals plot, and here we see the residuals plotted separately for carrots versus chocolate, and it looks like the chocolate dots, so the black dots, are going down with increasing predicted RT values, whereas the carrots are increasing with increasing predicted RT. And then we have in panel C the residuals histograms. There are 2 histograms overlaid on top of each other, one for carrots and one for chocolate. Both of these histograms appear to be very nicely Gaussian distributed. Back to the text. What do you think of the model results, the beta values and visualizations? The predicted data shown in panel A as lines appear to have systematic estimation biases. For the chocolate category, so that's the black line and dots, the predictions are too small for low brightness levels and too large for high brightness levels. Vice versa for the carrots category. Panel B reveals that something is amiss. The residuals should look like a shapeless cloud when plotted against the model predictions, but the black dots clearly decrease while the gray dots clearly increase. In fact, although the overall correlation for both categories pooled together is R equals 0, the correlation within each category is around R equals 0.5 or minus 0.5. The absolute value of R is around 0.5. Code to compute and print these correlations is in the online code. This reveals a serious problem with the model, and we should not interpret any results from this analysis. On the other hand, the per category residuals histograms look great, showing that histograms alone are insufficient to diagnose problems. Do you have an idea of what the problem is and how to fix it? Please take a moment to think of an answer before listening further. Some insight into the nature of the problem is that the predictions look reasonable within each category. Certainly not ideal, but it's not like the predicted values increase with brightness or are completely flat. In other words, the 2 main effects in the data, brightness and category, appear to be captured by the regression model. Have you figured out the problem yet? There was no interaction term in the design matrix. Footnote: I am not ashamed to admit that I accidentally forgot to include the interaction term when writing the code, and I didn't realize that there was a problem until I saw the residuals plot. I then decided to incorporate my mistake into the text as a learning opportunity, both for you and for me. Back to the text. There was an interaction term in the data simulation, so beta 3 in equation 15.33, but no interaction term in the design matrix. As you know, the interaction term is literally the element-wise product of the 2 variables. Recreating the design matrix using the code below is the only necessary change to produce figure 15.10. Here we have some code that is similar to code for creating the data frame design matrix that I described earlier. So variable df equals pandas.dataframe, and then I input a dictionary. The first key is brightness with value brightness. And then we have label category equals category. And then I have another one for interaction, and that is set to brightness star category. In R, you can replace the plus sign with an asterisk to get the interaction term and both main effects. So here's a line of R code. We have model equals LM, and then the first input is RT tilde brightness asterisk category. Remember, previously it was brightness plus category. And the second input is data.frame df, RT. This paragraph references figure 15.10, which shows the same visualizations as 15.9, but using a design matrix that includes an interaction term. Panel A shows the scatter plot with the observed and predicted data. In this case, the lines for the predicted data, the best fit lines, are both decreasing for both carrots and chocolate, but is decreasing more strongly for chocolate compared to carrots. And in the residuals plot, we no longer see any visually obvious relationship between predicted RT and residuals value for either category. The residuals histograms in panel C actually look less Gaussian than they did before. Back to the text. I'm sure you agree that the results in figure 15.10 are much better. The model predicted lines in panel A more closely match the observed data, and the residuals scatter plot in panel B have no clear structure. Indeed, the correlations are now R equals 0 for the overall and within category groupings. Interestingly, the residuals histograms are now slightly less Gaussian than before, but all other quantitative indicators of model validity are much better. The coefficients are also a closer numerical match to the simulation parameters. Beta 0 equals 603, beta 1 equals minus 1.99, beta 2 equals 82.3, and beta 3 equals 2.87. The beta 2 term had the wrong sign in the model without the interaction term, which is another indicator that something was horribly wrong with the model specification. Section 15.10.3, Example 3, two continuous regressors. This example will focus on storing and representing data with two continuous regressors. In this fake data set, I simulated exam scores from 30 students who reported the number of hours they spent studying for an exam and the average number of hours they slept per night in the week leading up to the exam. My hypothesis, which is confirmed by the data because that's how I created the data, is that spending more time studying increases exam scores only when students are getting enough sleep. Footnote. This seems like a reasonable relationship, but the history of science is full of claims that seem true but are disproven by rigorous experiments. Back to the text. For this example, I put all of the data, including the DV and the design matrix with an intercept term, into one pandas data frame. This is convenient because all relevant data are stored in one variable, but it also means that we need to be careful with the regression code to prevent the DV from being included in the exage input into sm.ols. This paragraph references figure 15.11, which shows part of the data frame, including the DV and the design matrix. So this figure illustrates a data frame. I'm showing 10 rows here and 5 columns corresponding to exam scores, intercept, which is all ones, study hours, sleep hours, and interaction. Back to the text. The experiment has two continuous regressors, which complicates the visualization. There are 3 variables, and thus a scatter plot would be drawn in a 3D space. 3D graphs look neat, but rarely provide a good depiction of the patterns in the data. This paragraph references figure 15.12, which shows a 3D scatter plot of the data. It's difficult to find a view angle that reveals the patterns. There are 3 axes, one for average sleep hours, one for hours studied, and one for exam scores on the z-axis. We see a collection of lines organized in 3D space, but it's really hard to make out the patterns that these lines are depicting. Back to the text. Therefore, in practice, a data set with 2 continuous regressors can be visualized by discretizing one of the variables or using color to illustrate the second variable. If you have more than 2 IVs, you can break up the visualization into multiple graphs or pick the 2 most important IVs to visualize and ignore the rest. This paragraph references figure 15.13, which has 2 panels and shows 2 options to visualize the data set with 1 continuous DV on the y-axis and 2 continuous IVs. So in panel A, I have discretized the hours studied into 3 groups. So there's one group depicted in light gray circles for less than 4 hours studied. In medium gray triangles are the data for 5 to 6 hours studied, and in dark gray squares are the data for more than 7 hours studied. And then in panel B, I'm showing visualization by color, where each data point in the scatter plot is depicted in the location corresponding to hours of sleep on the x-axis and exam score on the y-axis, and the color of that dot corresponds to the hours studied, with dark blue corresponding to 2 hours studied and going up through green and orange and then into deep red corresponding to 8 hours studied. Back to the text. I won't show how to implement or visualize the regression on these data because that's your job in exercise 3. Section 15.11, Assumptions of Regression. The assumptions section. All parametric statistics come with assumptions, and regression is no different. Fortunately, the more you learn about statistics, the more the assumptions will look familiar. Indeed, many assumptions underlying the validity of regression are the same as those underlying ANOVAs, t-tests, correlations, and other parametric statistics. Linearity. Because the math of regression is strictly linear, only linear relationships can be measured by a regression analysis. If the relationships are nonlinear, then a regression will either fail to detect the relationships or will quantify any linear component of the nonlinear relationship. Either way, this can lead to misinterpretation. Domain knowledge and visualization will help you determine whether this assumption is reasonable. Independence. The observations should be independent of each other. Dependencies in the data can cause misspecifications or biases of the standard error terms and reduced generalizability. Normal and homoscedastic errors. The residuals should be normally distributed and should have equal variance across the entire range of the IVs. No strong correlations among the IVs. Extreme correlations among the IVs is called multicollinearity and prevents a numerically stable solution. But less extreme dependencies can still reduce the accuracy of the regression model estimation because the effects of each regressor are difficult to isolate. If you have strong correlations within the design matrix, you can consider dropping some redundant variables or combining them through averaging or a dimension reduction technique like principal components analysis. Perfectly measured regressors. All errors should be in the DV, not in the IVs. In practice, this is not really possible to attain because perfect measurements of anything in nature are rare. Nonetheless, it is important to realize that measurement errors or noise in the IVs will be attributed to unexplained variability in the DV. This increases the residuals, which can reduce model estimation accuracy and can introduce systematic biases if there are systematic measurement errors. I introduced this idea when describing the difference between regression and principal components analysis, that was figure 15.2. Sufficient variability in the DV. Because regression is based on predicting variability in the DV, a regression analysis only makes sense if there is variability to predict. For example, the extreme case of a binary DV is not appropriate for a linear regression. Here you could use a logistic regression, which I'll introduce in the next section. Random and representative samples. This is the same assumption for all inferential statistics. The data should be drawn at random, individual observations should be independent of each other, and sample characteristics should be a good estimate of the population characteristics. In other words, any member of the population should have an equal chance of being included in the sample. Having a non-representative sample does not cause numerical problems for the regression, but it does limit the generalizability of the results to new data. As with all other statistical tests like ANOVAs and t-tests, regression analyses are fairly robust to minor deviations from these assumptions, especially as the sample size increases. Still, it's a good idea to check that your data conform to these assumptions and apply remedies when necessary, such as data transformations or selections. Section 15.12, Other Regression Models. The simple and multiple linear regression models that you learned about in this chapter are not the only kind of regression models. Fortunately, most other regression models are variants of linear regression, and therefore easy to learn if you have a solid foundation in linear regression from this chapter. Section 15.12.1, Weighted Regression. As you know, OLS stands for Ordinary Least Squares. An alternative to OLS is WLS, which stands for Weighted Least Squares. The idea is to apply weights to the data within a variable so that some data points will contribute more than other data points. As a simple analogy, consider that the, quote, ordinary mean, unquote, of the numbers 1 to 6 is 3. You can think of the average as the weighted sum of the numbers, with all three weights set to 1/3. Instead, let's set the weights to be 2/5, 2/5, and 1/5, under the assumption that the number 6 is an outlier, and we want to reduce its contribution to the mean without excluding it. Now, the, quote, weighted mean, unquote, is 2/5 plus 4/5 plus 6/5 equals 2.4. In a weighted regression analysis, the weights are determined either a priori based on some other variable, for example, indicators of the quality of the sensor measurements, or based on a normalized measure of the potential impact of each value on the results, with larger outliers having smaller weights. There are variations of weighted regressions, such as iteratively reweighted least squares, where the regression model is repeated multiple times, each time adjusting the weights until the regression results stabilize. The stats models library in Python has several functions that implement weighted least squares, including sm.rlm, which stands for Robust Linear Model. The R function to compute a robust regression is RLM, Robust Linear Model. These models are called robust because they are more robust to outliers, which you'll see in exercise 7. The main limitations of weighted regression are 1. Increased risk of overfitting because the weights are model parameters that are fit to one data set and are unlikely to generalize to new data. 2. Risk of biases introduced by putting too much weight on irrelevant data while reducing the impact of relevant data. 3. reduced interpretability of the beta parameters because each coefficient reflects a complicated relationship between the IV and the DV. And 4, increased computation time. Section 15.12.2, Piecewise regression. A piecewise regression is a nonlinear analysis that involves fitting separate regression models on different ranges of the predictor variable. Each piece is a linear regression, just like you learned in this chapter. The nonlinearity comes from the discontinuity between pieces. Figure 15.14 shows an example of a piecewise regression on simulated data. The nonlinear relationship between the DV and the IV can be captured by two linear pieces with a breakpoint at x equals 3. To run this model, the data are separated into two smaller data sets corresponding to x equals 0 to x equals 3 and x equals 3 to x equals 10, and then a simple linear regression is run on each data set. This paragraph references figure 15.14, which shows an example piecewise regression. We see a scatter plot showing a fairly tight linear relationship between x and y, but that linear relationship has two parts. There is one part that's from x equals 0 to x equals 3, indicated by a vertical gray dashed line. That has a steep slope, and then from x equals 3 up to x equals 10, we see also a very tight linear relationship, but the slope is much less. And the best fit line is actually broken into two pieces, so there's a bit of an elbow at x equals 3. Back to the text. In some applications, you may know the appropriate breakpoint. For example, in a study on students' mental health, where the breakpoint could be the age at which they begin university. In other applications, you may not know the appropriate breakpoint. Indeed, finding the optimal breakpoint may be the goal of the analysis. In such cases, you can use a model comparison approach in which you vary the breakpoint and evaluate model fit. You'll see an example of this in exercise 6, and the mechanism of parameter selection is based on a BIC comparison method that I will explain in the next section. Figure 15.14 shows two segments connected at one breakpoint. You can have more than one breakpoint. For example, one breakpoint for when students begin high school and another for when students begin university, perhaps a third breakpoint for when students finish university. Piecewise regression is useful when the relationships are locally linear but globally nonlinear. There is no upper limit on the number of breakpoints you can use, but if you are trying to fit data using more than, say, 3 or 4 pieces, then the function is probably sufficiently nonlinear that it might be better to use a nonlinear model or a polynomial regression. Section 15.12.3, Polynomial regression. A polynomial regression is used to model curves. They are particularly useful when modeling trends over time. In a polynomial regression, the columns in the design matrix are the x-axis values, for example, time, raised to higher powers. Thus, the first column in the design matrix is x to the power of 0, which is a vector all ones and is therefore the intercept term. The second column is x to the power of 1, the third column is x squared, and so on. The, quote, polynomial order, unquote, is the highest power in the design matrix. This paragraph refers to figure 15.15, which shows a line plot of x on the x-axis, and the y-axis is labeled x sub k. And then we have 4 lines corresponding to x to the power of 0, that's just all ones, a flat horizontal line, at y equals 1. And then there is x to the power of 1. This would be the next column in the design matrix. Of course, that's just a linear identity function. And then we have x squared, which is a parabola, and x cubed. Back to the text. Polynomial regression is actually still a linear regression model because the beta coefficients are estimated using linear methods, and because the model comprises scalar multiplication and sum. Indeed, the general form of a polynomial regression is shown in equation 15.34. This equation reads y equals beta sub 0 times x to the power of 0 plus beta sub 1 times x to the power of 1 plus ... beta sub k times x to the power of k plus epsilon. In other words, the coefficients are linear in the model. Only the regressors are nonlinear. Figure 15.16 shows two examples of nonlinear data and model fits by polynomial regression. This paragraph references figure 15.16, which shows two examples in two different panels of curve fitting via polynomial regression. Panel A on top shows a scatter plot where we see gray circles that follow a quadratic function, so a U-shaped function with a little bit of noise. And then there's a black line that shows the best fit of a second-order polynomial. And then in panel B below that, we see another scatter plot, also with light gray circles, and in this case, it's modeling something that looks something like minus x cubed. So on the left of the x-axis, we have the dots have a high value on the y-axis, then they go down, and then they go up a little bit, so there's a little bit of a shoulder, and then they go down again. There's some noise added, and a black line corresponding to the best fit third-order polynomial. Back to the text. How do you know what order to use? Models with higher orders, that is, more x to the power n terms, will fit the data better, but also have a higher risk of overfitting. Figure 15.17 illustrates the concept. The same data were fit using polynomial models of different orders. Clearly, an order of k equals 1 is insufficient to capture the curves in the data. The model with k equals 16 fits the data much better, but maybe the fit is too good. The risk of overfitting is high. This paragraph references figure 15.17, which shows polynomial fitting on the same data using different order parameters, so different complexity of the regression model. There are 6 panels in this figure arranged in a 2x3 matrix. We see a scatter plot of light gray dots with the same data shown in all 6 subplots. Each subplot or panel shows the data fit with a polynomial regression of different orders. So we have order 1, this corresponds to just a straight line, so just a linear fit. And then we have order 4, which seems to model the curves of the data better. Order 7, 10, 13, and up to order equals 16. Now order 16 shows the black line kind of bouncing all up and down, especially towards the end, towards the rightmost part of the data on the x-axis. The concept illustrated in this figure is that as the order increases, the best fit line is capturing more of the variance of the data, but there is a risk that we are just overfitting noise, so explaining too much noise, therefore making the model be less generalizable to future data. Back to the text. One solution is to fit many models of varying order and compare them using the Bayes information criteria, often abbreviated BIC or BIC. Here is the BIC formula. Equation 15.35 reads BIC sub k equals n times the natural log of the sum of squared for epsilon plus k times the natural log of n. K is the order of the regression model, and n is the number of data points. the SS epsilon term will trivially decrease as more regressors are added to the model, but the second term will increase with the number of parameters, thus acting as a penalty for increasing model complexity. The order with the smallest BIC value corresponds to the quote-unquote optimal model that fits the data best using the fewest parameters. Footnote: because the numerical value of SS epsilon depends on the data values, you can only apply the BIC comparisons on different models of the same data. Data transformations may change the BIC while preserving many regression characteristics. You'll see an example of this in exercise 12. End footnote. Figure 15.18 shows an example BIC plot for the data that I described in figure 15.17. The optimal order corresponding to the minimum of the BIC function occurs at k equals 3. Smaller orders, that is, simpler models, do not capture the data as well, whereas larger orders, so more complex models, have more parameters that are desirable. You can confirm in the code that commenting out the k log n term produces a monotonically decreasing BIC. In practice, you would produce a figure like figure 15.18 and then rerun the analysis using only the model with k equals 3. This paragraph references figure 15.18, which shows the results of a BIC analysis on a range of polynomial regression orders using the data that I described in figure 15.17. We see the polynomial order on the x-axis ranging from 0 up to 16, and the y-axis contains the BIC value, which ranges from 90 to about 145. The BIC function starts off high for low values of polynomial model order, and then drops down to 3 with a value of around 90, and then it creeps up from there. So the minimum of this function corresponds to a polynomial model order of 3. Back to the text. I wrote quote-unquote optimal in apology quotes because the BIC should not be blindly trusted. There are other formulas for comparing model orders, such as the Akaika information criterion or cross-validation, and the various algorithms do not always converge to the same optimal order. Furthermore, noise or small sample sizes can make the BIC results less reliable. For example, you might see multiple minima, in which case you can use the leftmost minimum. Thus, in practice, you should use a combination of qualitative, so domain-specific knowledge and experience, and quantitative, the BIC, the AIC, or cross-validation, methods to select a model order that balances model fit with generalizability. Implementing polynomial regression. Python first and R below. For the full suite of model evaluation measures, build a polynomial design matrix. You can see the online code that produces figure 15.15 and use sm.ols as you would for any other regression. But if you only want the beta coefficients and the predicted data, you can use dedicated functions in NumPy. So here we have the function numpy.polyfit. So we have I create a variable polycoefs for polynomial coefficients. Polycoefs equals numpy.polyfit with 3 inputs, x, y, 2. The 2 at the end indicates that we want a second order model. And then we generate the predicted data, and here I define variable y hat equals numpy.polyval with inputs polycoefs and x. The third input into the polyfit function is the order of the model. In the example above, the variable beta coefs will contain 3 numbers corresponding to the beta coefficients in the model, y equals beta 0 plus beta 1x plus beta 2 x squared. R does not have an exact match to NumPy's polyfit and polyval functions. Instead, you can use the poly function to construct the IVs and LM to fit the model. For example, the code below will design a second-order polynomial regression and then generate the predicted values. So here I define variable polycoefs equals LM, and the input is y tilde, function poly with inputs x, 2, raw equals true. And then we generate the data using the following line of code. Variable y hat equals predict, and then the inputs are polynomial, and then coef equals polycoefs, x. Section 15.12.4, Logistic Regression. I wrote at the outset of this chapter that regression is designed for a continuous DV and at least one continuous IV. Logistic regression is designed for analyses involving a binary categorical DV. Examples of categorical DVs include accuracy, so true or false, gambling outcomes, win or lose, and medical diagnoses, presence or absence of tumor. The idea of logistic regression is to predict the probability of an observation being drawn from one of two categories, dummy-coded as 0 and 1. Start with a typical linear regression model, but instead of predicting the DV directly, predict the natural log of the odds ratio. Now, I have not included a full discussion of odds ratios here, but it is the ratio between the probability of an event happening to the probability of the event not happening. For a binary outcome with probability p, the odds ratio is p divided by 1 minus p. This leads to the regression model for the probability of an event. Notice that the right-hand side looks like a typical linear regression model. This paragraph references equation 15.36, which is the equation for a logistic regression model. The equation reads the natural log of the quantity p divided by 1 minus p equals beta 0 plus beta 1 x1 plus ... plus beta k xk. I guess you have two questions. Question 1. Why take the odds ratio and not the probability itself? There are several reasons. Among them is that linear combinations of regressors can span a large range of values, yet probability is restricted to 0 to 1, while the odds ratio extends from 0 to infinity. Question 2. Why take the log of the odds ratio? There are several reasons, including the odds ratio has a lower bound of 0, while its log spans all real numbers. Log odds is symmetric. For example, an odds ratio of 2 and 0.5 are reciprocals but are asymmetric around 1, while the natural log of 2 equals minus the natural log of 0.5. And the log of small values have a larger range and are easier to work with in optimization problems. This paragraph references figure 15.19, which shows two lines in the same plot. We have on the x-axis the p value, so a probability value, and on the y-axis we have the probability ratio, either raw or log. There is a gray line that corresponds to the odds ratio, so p divided by 1 minus p. And that's a gray line goes from 0 to 1, but with this y-axis scaling of minus 9 to plus 1, it barely goes up. So it almost is a flat horizontal line, but it does go up a little bit. And then there's a black line corresponding to the natural log of that odds function. So the log odds. That one goes down from minus 9 in this plot up to around minus 1. So the span is much larger. The range of values on the y-axis is much, much larger for log odds compared to just the odds ratio. And the idea is that by stretching out small probability values, log odds are numerically easier to work with optimization problems. Back to the text. Anyway, to continue working with equation 15.36, we need to isolate p on the left-hand side. Here we have two equations, 15.37 and 15.38. The idea is that we are just doing some algebraic manipulations of 15.36, that's the equation for logistic regression, and the goal is simply to isolate p on the left-hand side to solve for p. So equation 15.38 reads p equals 1 divided by the quantity 1 plus e to the minus the quantity b0 plus beta 1 x1 plus ... beta k xk. I skipped a few steps between equations 15.37 and 15.38, but that's just a bit of algebra that you can work through on your own. Remember that linear regression is limited to linear operations on the regressors. Here we have nonlinear operations acting on the regressors. That's not a problem statistically, but it does mean that the left inverse method is no longer valid. Instead, the regression terms are computed through iterative nonlinear methods such as gradient descent. Another implication of these equations is that logistic regression does not directly output binary categorical predictions. Instead, it outputs the probability that each observation belongs to category 1. Depending on the goal of the analysis, you could directly work with those probability values or make a binary classification using p less than 0.5 for category 0 and p greater than 0.5 for category 1. Example. Earlier in this chapter, I simulated data showing that spending more hours studying was associated with higher exam scores. I'll modify that example slightly. Let's say the exam is pass-fail, making the outcome binary, and I will remove the sleep factor for ease of visualization. The number of study hours was simulated as 100 random numbers drawn from uniform distribution between 0 and 10. The probability of passing was defined according to equation 15.39, which reads p equals 1 divided by the quantity 1 plus e to the quantity s minus 5, where s is the number of hours studied and p is the probability of passing the exam. I then generated a random number from a standard uniform distribution for each student, and if that random number was greater than the value of p given s, they passed the exam. Here's how that looks in code. Here we have a few lines of Python code. I define variable study hours equals numpy.random.uniform 0, 10, n, and then we have the generating equation, which is also called the forward model. Here the code reads variable passProb equals 1 divided by the quantity 1 plus numpy.exp of minus the quantity study hours minus 5. And then we have random pass-fail according to the probability function. That line of code reads variable passed exam equals numpy.random.rand n less than passProb. So essentially what we're doing is generating some random study hours, pushing those study hours through equation 15.39 to define the probability of passing, and then each student randomly passes or fails according to a randomly generated number, and whether that randomly generated number is less than or greater than the computed pass probability. Okay, and then we have a couple lines of R code which are the same, although the syntax is very slightly different. The rest of the regression is similar to setting up a linear regression, except that the fitting function is different. So sm.logit in Python and glm in R. So here we have Python code, variable x equals numpy.vstack with input tuple of numpy1's n and study hours. That creates the design matrix x. And then we have variable model equals sm.logit with two inputs, past exam and the design matrix x, and then .fit for the method. And then there's a couple of lines of R code. Here we have variable df equals data.frame, x equals study hours, and y equals past exam. And then variable model equals glm with y tilde x, data equals df, and family equals, in quotes, binomial. Notice that the regression model is based only on the binary past exam variable. The probability values passprob are the ground truth to which the model does not have access. The overall model and the two coefficients, so beta 0 and beta 1, were statistically significant, and the results can be visualized by generating predicted probability values across these study hours. This is illustrated in figure 15.20, which shows the results of this logistic regression analysis. We have a scatter plot with gray circles. Those correspond to the observations, pass and fail, where fail has a value of 0 on the y-axis, pass has a value of 1 on the y-axis. The x-axis of this scatter plot shows the hours studied, ranging from 0 to 10. The y-axis is the probability of passing the exam for the predicted data or the actual outcome of the exam, so 0 or 1 for fail and pass. What we see in this plot is that all of the observations, so all the dark gray circles, are either on y equals 0 or y equals 1, with a higher concentration of fail outcomes towards the left, so fewer hours studied, and a higher concentration of pass outcomes, so y equals 1, as we go to the right, so hours studied increases. And then we have a black line corresponding to a logistic curve. This is the predicted data, the predicted probability, the outcome of the logistic regression model. It's a sigmoid curve, so an S-shaped curve that goes from 0 all the way at the right up to 1 all the way at the left. And the midpoint is somewhere around 5 hours studied. Back to the text. There are many details and extensions of logistic regression that I am omitting here, but I hope you are now comfortable with the basic foundation of implementing and interpreting logistic regression. Section 15.13, this contains the exercises. As you know, I have the solutions to all the exercises as videos on my YouTube channel. End of chapter 15.